Okay. Thank you so much for this. And let's start today's session. Distinguished guests, dear colleagues and fellow researchers, good afternoon, and welcome to this branch venue. It's my distinct honor to host this afternoon session, where we will delve into the exciting advancement and the progress in science and biomass conversion. Firstly, I would like to extend my warmest welcome to all of you. Your presence here signifies the shared passion and commitment to pursuing the boundaries of knowledge in our field. This forum is a platform for us to share our listed findings and inspire each other towards greater achievements. Before we officially proceed with the activation, I would like to take this opportunity to introduce some of our esteemed guests, an exceptional lineup of this in this field, who have graciously accepted our invitation to attend and provide their insights. First, we have Professor Pan Xuejun. Thank you, Professor Pan. Professor Pan is the Villas Distinguished and Douglas D. Sorensen Professor from the University of Wisconsin-Madison. Professor Pan heads the Lab of Bioenergy and specializing in research on pretreatment and fragmentation of lignin cellulosic biomass and chemical conversion of lignin cellulose to chemicals and liquid fuels. He is awarded the Fellow of the American Institute of Chemical Engineers. And we also have Professor Tong Zhaohui, also known as Julian Tong. Professor Tong. She is the James C. Barber Faculty Fellow and Professor from the Georgia Institute of Technology. Professor Tong leads the Lab of Bioprocess and Products, focusing on research in sustainable materials and catalytic conversion. She has developed innovative technologies for producing chemicals, energy, and fuels from renewable resources. She is also the recipient of the 2014 Florida Section American Society of Agricultural and Biological Engineering Outstanding Young Researcher Award. Furthermore, we have Professor Jeremy Luttebacher. Thank you, Professor Luttebacher. He is from École Polytechnique Federal de Lausanne. Professor Luttebacher leads the Lab of Catalytic Processing, specializing in research areas such as biomass conversion, heterogeneous catalysis, lignin chemistry, biocatalysis, and bioplastics. He is the recipient of the 2021 ACS Sustainable Chemistry and Engineering Lectureship. And we also have Professor Wang Li. Thank you, Professor Wang. She's the Zhongzhi Endowed Professor from Professor Wang leads the Lab of Biomass, Energy, and Materials, focusing on research for lignin cellulosic functional solvents for innovative applications of and multi-scale and multi-perspective sustainable assessment. Before joining Westlake, she was a research fellow in the Center of Environmental Policy at Imperial College London under the Marie Curie Industry Academia Partnership and Pathways Scheme, and a senior research scientist at Dutch Shell. And lastly, we are honored to have three special guests from Thailand. Professor John Saka, Professor Nakong, and Professor Suti. Thank you for our special guest. And now let's proceed with the academic presentations. Today we have 2 sessions, a total of 12 presentations this afternoon. Each takes roughly 8 minutes and followed and allow for 4 minutes for discussions. And our first presenter is Zhang Bei, who will be sharing the research on lignin-derived 3D porous carbon materials for advanced environmental applications. Let's give a warm welcome.
Hello, thanks for having me attention today for this section. I'm Beijing from Zhejiang University, and today to share the lignin-derived 3D porous carbon material for advanced environmental applications. As we know, the carbon material have different dimensions, including the zero carbon quantum dot and the 1D carbon nanotube and 2D graphene and the 3D porous carbon. But generally, we prepare this carbon material from the petroleum fuels. With the development of our society, we perceive that we have a sustainable research on the modern based carbon. And in addition to the biofuel, so in our group, we highlight in this review paper, we highlight the preparation of the bio-based material. And we want to have a carbon material from lignin. And actually, I'm from the environment engineering field. So we concern about the environmental applications for the biomass derived carbon. So in the environment field, we have the biochar and the powder and the granular active carbon for the wastewater treatment plant. So here, it's a precise for tip of the carbon. In addition to the sludge collection and the absorption parts, we want to use the lignin-derived carbon for some advanced applications like the catalysis and the device. But they still have some problem. The issues including it's hard to dispersion and the collection. And for the biomass-derived carbon, they still have quite option for some emerging pollutants and also the limited catalytic performance. So we want to solve this issue by construct of the 3D power structures. Actually, the biomass itself, they have original structure like the wood. They have some power structures for the water transfer control exactly. So we can also use the property of the lignin, like the thermoplastic and the thermocyte performance to do the electrospin and the 3D printing. But the power structures and some research also developed the biomass component like the cellulose and also lignin to prepare the hydrogen and hydrogen. But most general strategy, we can use the template. So this template is like the metal form and also carbon form. So the carbon form topic is I want to highlight today. So when I start my research in Singapore, I just think about how we can construct the 3D porous carbon form from lignin. So how we can explore its properties. And as we know, the carbon form have 2 types. So firstly, it's open, and how we can use this lignin-derived carbon form for environmental applications. So I want to share my research progress today. So we use the biomass. I think it's abundant. It's a palm kernel share. It's abundant in South Asia when I stay in Singapore. So we use the hydrogen modification strategy to modify the lignin structure. And while we perform the high temperature pyrolysis, we obtain this 3D porous carbon form. It's totally different with the general basis. We can only obtain the powder the morphology. So we assume the synthesize strategy. So why we have lignin with the increasing temperature? They conduct the soften firstly by self-polymerization, and then the pyrolysis gas can be served as a blow agent to have the self-blow these 3D carbon form structures. And with the high temperature treatment, they can promote the graphitization process. The first application we explore is to the carbon dioxide because it's a sustainable strategy because we can use the biomass waste to the carbon from the photosynthesis and to promote the carbon dioxide. Our results also show that our strategy, they have a little bit high absorption capacity for carbon dioxide and the selectivity. So it's possible to use for the decarbonization strategy. Research gave us some idea. The lignin component is quite key parameters during my synthesize the carbon form. So we use the lignin waste, the craft lignin from the, and we compare our modification and the general directly pyrolysis. So we obtain the carbon form structures. So here it's a representative structure for the carbon form. They containing the cell wall and the ligament. So this ligament structure can enhance the strategy of this carbon material, and they still have some window. It's formed during art. So this is the representative structures for the carbon form. But if we use another the general strategy, we cannot obtain. So to analyze the structure here, parameters to affect such structure, it's a salt content in our lignin precursors. So we use the ash content to show these parameters. So of the salt, it restricts the formation of the carbon form. But even for some low content of the ash content, we cannot obtain the carbon form. So the lignin component is also another parameter to affect such formation. So we use the FTIR to identify after the hydrogen modification, it formed the carbon oxygen double bond, and we try to do the NMR. I think it's a most advanced technique for the like the lignin researchers, and we identify some oxidized lignin unit as a key component forming process. And for the applications, because our environmental applications, we concern about how about the graphitization process, because it's good for adsorption properties for the, and also their adsorption property, the performance, like the specific surface area and the electrochemical properties, because it's related to my application in the system. So we directly use the carbon form as the carbon form cathode to establish the electrophoton reaction to achieve the degree contaminants in our environmental field. And we found that even the mixture of the contaminants, they still have good performance with the short time to achieve the totally. And in this research, we synthesize the electrode from lignin and try to make them as advanced environmental applications. And the summary, I think it's a lignin topic today. We found that lignin is quite, it's unique in the biomass precursors, but in future, we want to prepare the carbon form from lignin to other, like the secretary, the other components, and it's still on progress in our research group. And in addition to the hard carbon material, hard flexible, and we are still pursuing this research. And thanks to my supervisor from Tokyo Tech and the currently supervisor Chen Baoliang from Zhejiang University. And
extractions affect your properties for your final product. Also, if
and we conduct the hydrosome treatment, so it means that the hydrosome treatment with addition of some modification, like I think we added the sodium hydroxide, so it's quite nice. So I think this process I think it's good for the formation our modification of the lignin structures, and it means that no matter the precursors, if the precursors containing lignin after the hydrosome treatment with our addition of the agent, so it's possible to for the formation of the carbon form. So this is the first question answer response. We try to identify. So we identified two parameters. The firstly, it's salt content. So because the salt content during the softening process, the salt itself, they will restrict, they will limit the fluidity of the lignin. So if we have the salt, so we can only obtain the carbon powder, not the carbon form structures. It's the first parameter. Another one, I think it should be the lignin structures. So lignin structure changed. So we try to use the FTIR to the NMR to identify exactly, but you know it's not uniform precursors, so we cannot control exactly like other units. So generally, I think we can obtain some idea from the lignin-derived carbon fiber. Actually, the fiber excess is without the self-blowing. And if we can make some pyrolysis gas or some pressure, and maybe we can make it microstructures. So it means that the thermal forming part is also another technique to control the formation of these structures. And the last question, why this lignin-derived because I'm not like the forest, so I try to learn some technique like to the NMR. But the problem for the biochar part, because we use a simple process, we just use the biomass and we do the pyrolysis on the low temperature, we obtain the biochar. But the performance is quite limited. It means that they have low adsorption property performance. So we try to use the little bit pure lignin component to synthesize these advanced materials. So we think that the lignin form electrode direction for environmental field, because we still have some electrode treatment for the degradation of the contaminants. So it's my response for you to your question. Thank you.
Right, thank you, Dr. Zhang. If answers. Do we have one quick question?
Very nice talk. And my question is, so your self-forming process generates larger pores and a few hundred micrometers. Is it the way that's any way you can generate meso size pores? If you can do it, it significantly improve the forms of your porous carbon, right?
Yes, exactly. Actually, they have a micro pore structures like a large pore size. Yeah. Actually, for the caption of the carbon dioxide caption, actually the micro pore is unique. So it means that actually they promote the formation of the micro pore structures, like a few nanometers power. But for the meso part from the 2 nanometer to 50, I think we need some technique. Yeah. Thank you.
What's the yield of carbon?
Actually, I think it's cut for the 800 Celsius degree. Maybe I think it'll be the summer stable. So after even with the high temperature treatment, I think they still have more than like 80% yield. Yep.
That means you still have a lot of residual oxygen.
I hope so. Actually, the sorry for the time limit. Actually, for the environmental field, the oxygen function group is good for the catalytic performance. Yeah, it's unique. Thank you.
Thank you again, Dr. Zhang. We have a certificate for you in memory of a great moment. Right. Thank you. So our next presentation is, our next presenter is Du Jian, who will be sharing the research on design and high performance lignin-based triboelectric material in self-powdered sensing. Let's give a warm welcome.
Good afternoon, professors. It's my great honor to share my research work here. And I'm Du Jian, come from Dalian Polytechnic University. My topic is design and application lignin-based triboelectric material in self-power. As you know, since 1962, the wearable device have attracted more attention However, this traditional wearable device usually required external power source, such as lithium battery. However, this battery usually needs the time-consuming charging process. So, if electric nanogenerators is also called TNG, novel technology, and this TNG mainly relies on the coupling of tribal electrostatic effect. Also, this TNG is composed of tribal positive and tribal negative materials. Based on this, electrical power can be formed by processing this device. So usually the tribal positive polymers such as lignin and cellulose. Here, since 2017, lignin was usually used as a nanofiller or tribal layer in the TNG. As you know, lignin is the second most abundant natural polymer because they have several advantages such as eco-friendly, renewability, and low carbon economy. However, the low tribal polarity of lignin. So the important thing is how to further improve the outer performance of lignin-based TNG. And the second one is due to the complex structure of lignin, how to reveal the relationship between the structure and the output performance. We will briefly introduce two research works. The work one is how to improve the polarity of lignin for better TNG. In this work, we found the electron cloud was enlarged. The enlarged cloud will be overlap during the friction, so more charge will. So from the XPS spectra, the carbon oxygen double bond and the iron ions with the state of 2 was detected, implying the strong interaction between the lignin and the iron. Also, from the potential surface potential, also demonstrate the more electrons. Also, from the calculation, the dial was also improved. The overall output performance of TNG improved about 4.6 times. Also, when the iron was replaced by other transition metals such as zinc, the output performance will also be enhanced, further highlighting the advancement of this strategy. So also, when applied as a sensor, our body movement can be detected, such as our throat, the elbow, and the ankle. So the next work is what kind of structure of lignin will show better TNG performance. In this work, the solvent extraction strategy was carried out. The LC acetate lignin, LC alkyl lignin, LC alkyl lignin, and acetone lignin, and the residue lignin was obtained. We can see from this table, the molecular weight was increased from about 1,000 to 6,000 during the extraction process. Moreover, the linkage such as A type was increased, and the B and the C type was reduced. Also, the S unit was reduced, and the G unit was increased. Moreover, the dipolar moment was calculated. We can find the different linkage, unites, and the molecular weight have different parallel movements. Moreover, from the dielectric constant, we can lignin with the ideal structure is more S unites, A-type linkage, and large molecular. Also, the results have confirmed this conclusion. The output performance can be improved about 17 times on lignin compared to pristine lignin. Also, due to the fast reconstruction and break of hydrobonds in water, the composite film can be reformed and reused 5 times. Also, when this sensor was applied in our body, when we write different letters such as B, C, and D, different signal can be obtained. Also, when this TNG was applied as a power source, the LED can light. Also, we have 2 key findings. So first one is by introducing the transition metal into lignin term, special electron charge can be adjusted. The second one is the lignin with unites, A-type linkage, and large molecular weight will also for better TNG. Okay, thanks for your attention.
Thank you, Professor Du, for the insightful presentation. Before we open up the free discussion, we are honored to have Professor Wang commentary.
Okay, thank you very much for the introduction. Actually, I'm not quite an expert in this field, so I may ask a stupid question, but it's also a learning process for me. So it's a very interesting talk and a very interesting application of the lignin. So I have like 2 questions to open up the discussion. So one is, I'm not quite sure of performance indicators you use to compare your sensing device with the other traditional polymer-based sensors. So like sensitivity or the lasting because it has the energy storage. So how do you define those performance indicators, and how is your sensor polymer based sensor? That's my first question. And second is you mentioned that the S-type units of lignin is the preferred lignin type for your application. Wondering how much of the yield you can get from the various types of biomass to get the S units lignin. Is the yield matters for your application, or the yield doesn't matters really? So that's the question. Thank you very much.
Thank you. It's a good question. In fact, due to the time limited, in fact, we have compared the output performance with previously work in the table, and I didn't show here. And the output performance we about in the at charging at edging performance, and is better performance by polymers based TNG. Yeah. The second question is about 2 or 3 doping amount was introduced into the cellulose during this work. Yeah, in the
as a base.
Yeah.
But you use S type of lignin extract from like the softwood.
Yeah,
the wood hardwood.
Yeah.
So what kind of yield you can get from the hardwood lignin?
What can you?
So the S-type lignin, how much of the yield you can get from your biomass source?
We have the industrial lignin.
Okay.
No, this lignin was not extracted by ourselves. We get this from the.
So the source is not
Yeah,
really
yeah.
a problem to fabricate the sensor.
Yes.
Okay, thank you.
Thank you.
More question. So you mentioned that you trying to study how lignin types and how irons are inserted in your factor T and G performance, right? So, but I didn't see, probably because of time limitation, you don't show that. So I just wondering, you make the film, right?
Yeah.
Using lignin and cellulose, right?
Yeah.
So I just want to know what's your experimental details, like because we cellulose membrane as well. So if you absorb the different kind of ions, depends on, like, you just drop on that, you absorb on that, depends on different way. They will affect your TNG performance because it depends on your roughness. There are many different type of the small properties they can affect your TNG performance. So that's the reason I want to ask you your experimental details, like how your iron and the cellulose lignin, how did you make, and how can you control? So like with your control, how can you make sure, like you are in the same, for example, if you use different way to add your iron, so probably your roughness, your surface area change it, so then your TNG will be changed. But that maybe it's not because of your lignin type. That maybe not because of your iron. Yeah, that's maybe some kind of comments and some kind of like questions. So
yeah, there are many factors in influencing the output. In fact, the SEM we have observed the surface is smooth because the lignin is doping amount 2% to 3%. So the smooth of CMC film is smooth.
So you use CNC make the film, right?
Yeah.
So you put your into your CNC solution and then casting from the film?
Yes, in the CMC solution, yeah.
Okay. So have you checked your smoothness? Because it depends on different your drying process.
Yeah.
You may get different roughness.
Yeah, we have measured it by the AFM, and the result I didn't put here.
Okay. Yeah. That's fine.
Thank you.
Hi, I had a question. I just didn't quite understand how you did this correlation between the length of the polymer and the S and G. What are you using to make this correlation?
Correlation?
You had this graph where you had 3 data points.
Yeah.
And you showed the effect on the slide.
Okay.
No, before, I think one more. Yeah, that one. So how did you get, how do you know that you have 1, 2, or 3 units?
Okay, we have calculated by this here.
Yes.
Okay. Here, and this 3 units.
Oh, so it's a stimulation.
Yeah.
Because what would be really nice is if you could actually synthesize, because you can make monomers, dimers, and trimers. Actually check that.
Okay.
And that would be, I think that would be quite nice.
Thank you so much.
This based on your simulation.
Right. Thank you all again for the very great questions and answers. Due to time limitation, we need to move on certificate to in memory of this great moment. Next presenter is Dr. Cao Yang, who will be sharing the research on glucose oxidation over active copper 0, copper plus sites stabilized carbon. Let's give a welcome.
Good afternoon, everyone. I'm Cao Yang. Oh, thank you. I'm Cao Yang, a postdoctoral fellow at the Hong Kong Polytechnic University. Today, I would like to take a moment to thank the organizing committee this opportunity to share my recently study about the glucose oxidation valence of copper sites stabilized by the lignin-derived carbon. So firstly, I would like to introduce about the biorefinery. We all know that biomass is an renewable resource, and it is classified as a source of carbon neutral energy. And the biorefinery can provide a sustainable approach to convert the biomass to chemicals and the biofuel. So for the biomass, it mainly consists of cellulose, hemicellulose, and it contains a long chain of 6 carbon sugar, and the hemicellulose is made up of both 5 and 6 carbon sugars, and they can be used to produce different chemicals through the catalytic conversions. So for the lignin is one of the most important aromatics in the planet, and the efficient conversion of to produce various valuable added chemicals and carbon-based materials. So here is a figure that shows here the catalyst from the renewable biomass, which can contribute to achieving the carbon neutrality for the low carbon footprint chemicals and the fuel production self-contained systems. So firstly, I would like to introduce one of my recently research about the lignin-derived carbon low valence copper site for glucose oxidation. I used a soft Euro method to nitrogen doped carbon, and for the lignin, I select the bioenzymic corn cobalt lignin. It is a commercial product from the Shandong Longli. And I also try other like the craft lignin and organic of lignin for the catalyst preparation. So I would like to firstly introduce the aromatic lignin. The lignin, Euro, and copper precursor will mix together, and after a high temperature process, nitrogen doped copper-loaded nitrogen doped carbon. And for comparison, we also prepared the copper-loaded carbon catalyst for So from the TM images, we can know that the copper-loaded nitrogen doped carbon has a nano-sized copper species ranging from 6 meters. And this catalyst mainly exposed the mint-like copper species, copper 111 plants. And without nitrogen modification, the catalyst has a large copper particle size ranging from the 12 nanometers. And we can, from the TEM images, we can know that the introducing nitrogen heteroatoms can stabilize the copper species, and it can also affect the mint and is exposed planets. Oh, sorry. So we also use the other techniques to evaluate the characteristics. We use XR, the XPS, and the exams to evaluate the chemical valence of the mental site. We find that the valence state of the copper site followed this order, and it showed that the copper-loaded nitrogen-doped carbon has more copper carbon or copper nitrogen coordination structures, and without nitrogen doping, we can find that more copper oxygen bonds formed. So it can also clearly demonstrate the effect of nitrogen doping for the enhancement. So we also evaluate the catalytic performance of the prepared catalyst. We select the glucose substrate, and the reaction was conducted at the 160 degree. for 30 minutes, and we use the 20 bar air to provide an oxidation environment. After the reaction, we can find that all the copper-based catalysts were active for the glucose oxidation to the gluconic acid at the carbon 1 position. So, and without the copper 1, we can get a high glucose conversion and a high yield of the gluconic acid. So for the oxidation reaction, it is very important to identify the reactive oxygen species over the surface. So we try to use different measurements to identify the real ROIs generated on the catalyst surface. Firstly, we try to use the KIE measurements to see, because we use the water as the solvent, so we try to use the D2O to significantly reduce to around the 39%. And so it may indicate that the water may participate in the oxidation reaction. So we also tried the scavenger test. We use hydroxyl radical scavenger, isopropanol, to see if the hydroxyl radicals or the main oxidizing species. So after the scavenger test, we find the glucose conversion also reduced. So it may also indicate that the surface OH species was a preeminent oxidizing species for the glucose oxidation. So for the investigate the surface reaction, we conduct the in situ Raman to analyze the surface species. And when conduct the in situ Raman and different reactions, firstly, we only introduce the oxygen. We can find the copper oxide and copper adsorbed oxygen species were formed during this process. And when we introduce both oxygen and the water vapor into the system, we can find two different peaks formed that can be corresponding to the copper OH species. So that clearly demonstrates the water may significantly affect the surface species formation. Nitrogen atmosphere, there is the glucose conversion is very low. So both water and oxygen are very important for the oxidation reactions. So to clearly understand the electrostructures and the possible reaction pathways, so we conduct the DFT calculations. We select two models. One is the nitrogen copper-loaded nitrogen doped carbon, and another one is without the nitrogen dopants. So we can find that the electrostructure is quite different, and the introduce of nitrogen can promote the formation of electron-rich cuprosites, and the reaction pathways mainly follows the oxygen, OOH, and OH species that can double conform our reaction pathways, and surface species participate in the reaction. So here is the main mechanism. We found that the ROS generated over the catalyst surface, and which through a 3-electron transfer pathway for the glucose oxidation at the carbon 1 position. Here is another work. We use a different soft template to prepare the low copper loading catalyst. It also showed a high glucose conversion rate. So that's all my presentation today. Thanks for your attention. Thank you.
Thank you, Dr. Zhao. So we are ordered to invite Professor Pan to give a commentary insight.
Thank you. Very nice talk. Very interesting. Try to use lignin-based carbon as a carrier of catalyst to oxidize glucose into gluconic acid. Very nice study and talk. I have a couple of questions. The first one, so why you choose lignin as your carbon precursor? It's just you want to just use lignin because it's kind of bioproduct from biorefining, or you think a lignin-based carbon performs better? So that's the first one. The second one, so when you prepare the catalyst, you mix lignin, urea, and copper.
Yes.
And what's the rule? But I saw you use ethanol plus water as solvent.
Yeah.
So what the lignin is enzymatic.
Yeah. Automatically.
Why you use solvent ethanol plus water?
Okay.
The second question. The third one is how about the selectivity of your oxidation?
Okay.
So in addition to the gluconic acid, you target, you observe. What's the principle? Mechanism.
Okay.
Thank
Okay.
you.
Thanks for your next question. For the first question, why choose the lignin? Because lignin has many phenol-like groups. It can interact with our mental precursor by forming maybe a complex. I dissolved. I added the firstly lignin was dissolved in the ethanol, and I use the ultrasound maybe for 30 minutes, so we can get a highly dispersed solutions. So after that, I add the mental precursor to mix with the lignin solutions. So it can maybe there are abundance of oxygen containing functional groups. So it maybe contribute to dispose the mental species. And secondly, because the lignin has a high carbon content as compared of the cellulose and hemicellulose, we want to get a high yield of the high yield production of the catalyst. So we select the lignin as our carbon precursor. For the second question, solvent. Yeah, solvent. I use ethanol as the solvent because lignin can be very dissolved in the by using long-term ultrasound.
So that's the raw lignin we have. So
yeah, I use the because the molecular weight of this lignin is very low, around 900
Good afternoon, everyone. I'm Xiuhai Zhu from DSCP. Today, my presentation topic is exploring non-cyclic alkyl ether structure in lignin. I will introduce my work from 4 aspects. Sorry. First is background of my research. As so far, the structure and the biosynthesis process of lignin has not well understood. According to the widely accepted hypothesis, lignin are derived from 3 monolignals: the hydroxyphenyl unit, gaseous unit, syringel unit. They can give rise to these units during lignin polymerization. The lignin polymerization can occur through the radical coupling reaction. By this reaction, these units can attach with one another by a series characteristic linkage, such as beta-O4 linkage, beta-beta linkage, and beta-5, beta-1 linkage. All these, the formation of all these linkage are related with the quinol method intermediate. After oxidation of the monolignal, several quinol method can be formed through beta-O4 coupling, beta-5 coupling, beta-beta coupling, beta-1 coupling. Subsequently, they are reionized by the addition of water or hydroxy group from external or internal molecule. As a result, the free phenolic structure can be formed. This structure can be further oxidized and coupled with a new monolignals to extend the lignin chain. So we can see the reionization step of quinol method is important for the formation of lignin. They will produce different types of lignin structure and also different isomeric form of structure in lignin. Since the beta-O4 structure are most abundant lignin, so we focus on this beta-O4 bonded quinol method as a key point in my research. Depending on the types of the nuclear phenols, different types beta-O4 structure can be formed. As you can see, if water touch this beta-O4 bonded quinol method, the normal alpha hydroxy beta-O4 structure can be formed. If the phenolic hydroxy group attach this structure, the alpha O4 beta-O4 structure can be formed. Also, if the aliphatic hydroxy group from the carbohydrate attach this structure, the well-known LCC structure can be formed. All the existence of all these structures were already confirmed by the previous research. By following this logic, the aliphatic hydroxy group from the lignin chain can also possible to attach this quinol method to form the aryl ether structure. In our previous research, we proposed a qualitative structure model of spruce milled wood lignin. There are half of branching points located at the aromatic ring. Also, whereas the rest of the branching point was calculated at the aliphatic side chain. We tentatively assigned this branching point as the aryl ether structure. However, the further structure evidence to confirm the existence of such structure have not yet presented. So in this research, I employed the several definitive aryl ether compound and animal technique to exploit the existence of this structure and exploit its biosynthesis. This structure has aryl ether moiety at the alpha or gamma position and with additional beta-O4 or beta-beta structure. As you can see, the spectrum of milled wood lignin, the resonance of a modern compound match well with the spectrum of milled wood lignin. So we can assign the specific region to several aryl ether structures, especially for this alpha or aryl ether beta-O4 this structure was existing in the milled wood lignin. As we already described, the existence of the formation of this structure may be related with nucleophilic addition to the Quinol method. So we did the modern compound studies to explore the formation of this structure. We synthesized several Quinol method modern compound, which is different at the beta isophine aromatic ring, and also use animal to get the detailed structure information for this Quinol method, and also we to do the reaction for the Quinol method with the water, methyl ethyl to mimic the formation of this structure, and use UV spectrum to monitor this reaction and analyze the product with animal. Because the disappear Quinol method can fit well with the first order reaction. So the half-life time of the Quinol method, the disappearance of Quinol method can be calculated. So we use the half-lifetime of Quinol method to calculate the reaction rate of this reaction. From the reaction rate, we can see the nucleophile react faster in the order of ethanol, and Quinol method react faster in the order of GH, GS Quinol method. The effect of nucleophile is larger than the effect of beta isophine aromatic ring. This is the conclusion for the reaction rate. For the distribution of diastereomers of corresponding beta-O4 product, we can see the product of area ether product can be obtained by increasing the number of methoxy group at the beta isophine aromatic ring, and also we can increase the number of carbon atom of the nucleophile to increase the uracil product. On contrary with the reaction rate, the effect of beta isophine aromatic ring is larger than the effect of nucleophile. So based on this the results from model compound, we propose the formation of this aerial ether structure. We can see, actually, we propose that the formation of aerial ether structure is more likely formed in the early stage than the later stage for the ligninification. Also, if the aerial ether structure exists in lignin, it should be mainly exist as the uracil form. Last is the conclusion of my research, and my further work is continue with DHP and ordination to further confirm this structure and exploring its biosynthesis in lignin. Last, I will acknowledge the lignin experts for their valuable suggestion, and also acknowledge their financial support. Thanks for your attention.
Right. Thank you. Thank you. It's very good timing. Firstly, we're honored to invite Frank to give insightful comments.
Yeah, so I think that was very nice. There's a number of points. I think this is an interesting field because there's this big disagreement.
Yes.
Right. So one question is, where do you stand on the maybe you can go back to one of your early slides. So you show this DBDO as a potential branching point.
Okay.
This wasn't a direct. So my understanding, yeah, excellent. So there you show here that the phenolic position can keep polymerized for the DBDO, right? And that's notable. So I've heard in a bunch of cases that it's not directly my research, but that can no longer polymerize, that the reactions stop there. Notably because you can't form a quinone-methide anymore.
You mean this?
So once you hit the DBDO, that phenolic position becomes terminal.
Actually, yeah. For the phenolic, this phenolic DBDO or non-phenolic DBDO is still in debate, right? From my understanding.
Well, yeah.
Sorry.
So exactly. So what's your take on it? Because my understanding is there you can't form a quinone-methide anymore. And so there you're blocked in terms of the reactivity.
Actually, for from my understanding, the formation of DBDO is also related to the Quinol method. But once the DBDO is formed, yeah, for this position is still, I think, still in debate.
Depends who you talk to. So your take is that you can still form it there, because the other argument is that some of these positions you can form if you use model compounds. Once you have the full lignin and a real polymer, it's not the same, and the steric hindrance just leads to.
The polymer, you mean the DHP, or
if you actually have the whole polymer,
the whole polymer?
You can get these reactions. So this is also the same argument, because the conflict often arises between the fact that you observe something with model compounds, but then you don't observe it in the real lignin. And the issue is that if during lignification the polymer is long, that you have issues of steric hindrance and things like that, and it doesn't happen. So some of the compounds you observe, have you actually observed them in real lignin or not? That was sort of unclear.
The real lignin.
Yes. So I saw some NMR spectra, but
so actually I use the mildwood lignin,
mildwood
lignin. Yeah, that's why I cited actually I exploit the existence of this structure in mildwood lignin. So we are not sure whether the precise on the lignin will produce this structure. Maybe during mild lignin, this area structure also could be produced. This is still, we still exploit the other hypothesis for the formation of area structure. But from a perspective, from the perspective of the radical coupling, we try to exploit the formation of this area structure.
Because it's the same, right? Here, the 504 shouldn't form either. The one you show there, right? That position should also be blocked. So they always observe in the DBDO structure, it's always terminal. So yeah, that one there. That one probably doesn't happen either. Or that's still controversial.
Actually, sorry, I think this structure, maybe I need to modify. I think maybe something wrong on this process. I'm not sure. So can we discuss further after the meeting? So yeah, since this is complete, I cannot catch the position.
And maybe one last question. So you were talking about the stereochemistry.
Yes.
The lignin. And so my understanding is that the lignin is completely racemic. So I didn't completely understand your argument. Do you think these linkages only form on one of?
Actually, the lignin is I exploit the uracil and serial form, the diastereomers of lignin and of the beta oval structure. So for the lignin, yeah, most people think lignin is racemate. Yeah, but I think the existence of the uracil and serial form does not influence the racinity of lignin.
Yeah.
Even the ratio of uracil and serial form is not equal to 1.
So you're proposing that, but based on model compound study.
And not only the model compound, we also actually in my previous group we also investigate the lignin by the organization to try to investigate the stereochemistry of lignin.
Yeah.
And the conclusion is lignin is recent.
It just gives straightforward answer.
No, so here I'm really trying to understand. So it's not I'm not contesting it, but there you have so you didn't measure the ratio to be, the ratio was different than 1
The ratio
of stereoisomer
for the modern compound,
for model compound. Well, both for real lignin and model compound.
Actually, I have the related result, but yeah, I did not mention in this presentation. This is the time is limited, and in the lignin, if sorry for the time waste. For after the organization of the lignin, we can see the different uracil and this uracil and serial ratio in lignin. For it depends on the wood species.
Okay. What technique do you use for that?
The organization.
Oh, okay.
The organization, since the organization, after the organization, the side chain, the steel chemistry of side chain in lignin can be kept, and we can calculate the ratio of uracil and serial ratio from the product. And for the softwood, the uracil preference can be obtained. Hardwood, the uracil serial ratio is higher than 1. It may be related with the height. This is a conclusion.
Okay. Okay.
But in this study, I just since the time limited, I just show the existence of aerial uracil and try to understand its formation. Because and since it's the time limited, I didn't put the related steel chemistry results.
Okay. That's very interesting. Sorry, I don't want to take too much time. When it's interesting, you have a lot of questions.
For this, we'll leave further discussion to the coffee break. Thank you again, Dr. Zhu. And here is the certificate to Mario. Our next presenter is Dr. Niegen Kuo. She'll be sharing the research on catalytic valorization of lignin cellulosic biomass and mechanisms. Let's give a warm welcome.
Good afternoon, everyone. My name is Niegen Kuo from Qingdao University of Science and Technology. My presentation is catalytic valorization of lignocellulosic biomass and mechanism. This is the main path I will. As we know, the organic substances we can get from plants include plant metabolites and lignocellulose, and the plant metabolized is resources limited, such as terpenes, and the lignocellulose can be hydrolyzed into furans, ketones, ions, phenols, bases, and alkenes. So precise molecular design and catalyst creation, these substances can be further converted into high value-added compounds. We used these compounds from lignocellulose to synthesize high-density jet fuel precursors using addition concentration. This is the key step for the synthesis because it constructs polycyclic compounds and determines the carbon skeleton of the fuels. Then hydrogenation and hydrodeoxidation of these precursors to settle the hydrocarbons. This to improve the energy and the storage stability of the fuel. The political compounds in the saturated hydrocarbons are more popular because it can improve the low temperature performance. Think about the key reaction step of addition. Strong acid or bases are effective and take the step of hydrodeoxidation into consideration. Acid catalysts are preferred and have the potential to achieve multi-step reactions in theory. So what kind of acid catalyst can accomplish the effective addition reaction for biofuel synthesis? Firstly, it must strong acid to initiate the possible carbon-carbon coupling reaction. Then anti-carbon deposition, water tolerance, and molecular control are also required. The commonly used acids such as heteropoly acid, for example, phosphorostatic acid, we often call the HPW. The zeolite H-beta ZSM5, HY, and MCM SBA series. The reasons embraced 15, 9. First, let's look at the HPW. It is a super acid solid acid. The acid strength is stronger than the sulfuric acid. However, its surface area is small, only 5 square meter per gram. So the first of all, we have to increase the surface area. In our previous work, we support the HPW on MCM41 to catalyze the demand of terpene, and the support amount could be 80% message of support, which is a big supporting amount. But HPW is easily soluble in polar solvent, so acid leaching is a problem to be need to be solved. We developed a highly stable, efficient, and water tolerant SB16 confound HPW catalyst and applied it to counterbolt catalyze cross condensation of hexapentanol and cyclohexane. Look at the finger. We used alkyl imidazole to modify the surface of SBA16. It gives a phobic environment and alcohol to the HPW, and this makes it has a stable reusability in the reaction. Also, the stability of the catalyst is enhanced. The loading amount is limited. So we developed a new method to make the catalyst using HPW. Here we used half NM to doping supported HPW and used it to catalyze the idle condensation of lignocellulosic ketones mixture to make a high density jet fuel. Look at the TM imaging. The particles are dispersed eventually on the surface of MCM41. Why the diameter of the particles is about 1.76 nanometers, which is very close to the size of HP itself, indicating it is a successful doping one. This catalyst has a gold float state and on the water, and with the half doping, the water connect angle became larger. By half doping, the new strong Lewis acid was created, and the catalyst has present gold stability on anti-cooking and water tolerance. the summarize these two works, for the addition or condensation, two factors important. One is the acid property, and the other is the water tolerance. We also mix the resins to use to the co-conversion of lignocellulose derivatives. Controlling the feedstock mass ratio, the phosphoricity of the catalyst is dramatically improved. Although this catalyst has it shows the significant cooking and is stable in the reaction cycle. Besides this, we investigated the competitiveness of this feedstocks in the reaction using DFT calculation and basic kinetic reaction. Besides this, the medium and weak acids are also useful for the high process. We use the PT Vox T02 to synthesize hexanol. To the electron transfer from W to PT to make appropriate strong bronzed acid and appropriate PT size reaction or to oriented regulation this reaction. Then we also developed a one-step reaction to synthesize from HMF using PT Supple 11. Other chemicals such as dialcohol and diacid, we also prepared. We hope have the chance to share to you in the future. Then hydrolysis, oxidation, coming coupling reaction, and hydrogenation are can be used to convert to jet fuel and fine chemicals. That's all. Thank you.
Well, thank you, Dr. We are honored to have Professor to give insight.
Very nice talk. So maybe because you go so fast, so catalyst, so solid catalyst, right? So so my question will be, if you because right now you use the small molecules to synthesize into the jet fuel, right? You're doing the additional reactions, right? So if you're thinking about, because your molecules need to be, if you're thinking about sustainability, right? Break down polymer to get the small molecules, right? There's another way. It's like you break down the like lignin or other long chains to get the jet fuel. So maybe I just want you to thinking about like if you way, what is the advantages of your way to do that? Because you can also use the acid catalyst to do depolymerization as well, right?
Yeah.
So for the reaction right now you're showing here is additional reaction, right? Most of them. Thinking about, I mean, this will be really open questions. So additional reaction, so you need to have prepare the small molecules, right? So from high molecular weight, high chain, long chain, carbon chain polymer. So, I mean, I just don't want you, like, I know this is just open question. So how do you think about this question? Depolymerization or depolymerization?
Thank you. Very nice question. Actually, at present, we use the compounds that are formation of the compound from the lignocellulose. They are small molecules. In fact, the diphenyls is more welcoming, but now due to the cooking in the reaction, the yield is low directly from lignocellulose to make jet fuel. We are working use the lignocellulose oil to make jet fuel at present. This is a small progress compared to use the small molecule from lignocellulose.
Molecules you use for your synthesis, right, to the jet fuel. Is this small molecules commercially available? To get biomass?
Yes, at present we use the commercial one, but actually we willing to use the ones from lignocellulose. Maybe a serious reaction, a catamine reaction should be developed from plant such as corn, and to use several catalysts to complete this reaction.
Right. Thank you for the great discussion. Due to time limitation, we move on. And finally, we have a certificate for you. And next, we have our presenter, Dr. Liu Qiyu, who will give a presentation on the research high yield production of non-condensed lignin via effective deconstruction of lignin cellulosic biomass. Let's give a warm welcome.
Hello, everyone. I'm here to introduce my recent work. Today, I want to share my recent work. The topic is high yield production of non-condensed lignin via effective of lignin cellulosic biomass. I'm Qiyu Liu from Guangdong University of Technology. As we all know, lignin cellulose is composed of many, including hemicellulose, cellulose, and lignin. And those three components are different in characteristics and different in units, which makes them are different to be utilized in one conversion process. Therefore, in order to achieve full utilization of three components, we need to do an effective fractionation process to spread off them, especially with the native structure preserved. The native structure, especially the lignin native structure. The biomass fractionation method can be roughly divided into two types. The first one can be called lignin first, and the second one is cellulose first. Lignin first method generally use the depolymerization process to convert lignin into monophenols. This method can achieve a full utilization of lignin and with most of cellulose preserved. However, the lignin generally can be only used as a monophenols, which limits its application in some advanced materials. Cellulose first method has a very long history, which used in paper making industry. In this method, lignin was sufficiently removed, and the cellulose and hemicellulose can be sufficiently used. However, the lignin often generally the lignin cellulose condensation reaction and can be hardly used in the following process. My work is focused on non-condensed, actually to provide a non-condensed lignin with a high yield. The lignin condensation refers to hash reaction conditions lead to the cleavage of beta-O4 linkages and the formation of stable CC bonds. The condensation of lignin has many negative effects, such as the stable CC bonds make it difficult to depolymerize, and the decrease of active functional group limited its application in some materials, and the intensify lignin benzene is application as such as colorless film or something else. Therefore, non-condensed lignin is a valuable polymer due to the visible application pathways provides. In order to achieve in pollutants, infection-like cleavages and dissolving, as well as inhibiting the beta-O4 linkages cracking, we need to do something. However, under the mild reaction conditions, although lignin can be obtained with a low condensation, but the limited yield can be a challenge. Increased hash reaction condition can facilitate the cleavage of LCC linkages and obtain a lignin with high yield, but a very terrible condensation can be found. So it needs to find a balance between yield and structure. In order to achieve these challenges, I want to express my three work. The first one is reaction. The first one is reaction condition optimization, and the second one is reaction system design, and the third one is reaction pathway design. My first work focused on concentrated formic acid fractionation. The formic acid has we use the very concentrated formic acid with a concentration of 80%. This concentrated formic acid has a high solubility to lignin. Under the relatively mild reaction conditions to pre-treat biomass, more than 90% of lignin was dissolved in the solution, with the most isolated. Under the optimized reaction condition, the beta-O4 linkages can be well preserved, and this lignin can be into monophenol with a high yield of 28%. In order to achieve selective CC linkages without affecting beta-O4 linkages, we developed a new reaction system with a micro-assisted PTSOH fractionation. The biomass was treated in the methanol with assistance of microwave. We found that under these reaction conditions, before we used these two components to do the test, and found that under these reaction conditions, the beta-O4 linkages don't cleave the LCC modern components cleavage and the active energy of LCC linkages cleavage decreased from 100 to 63 kg per mole. So we think that this reaction system can selectively cleavage of LCC linkages. We use these two modern components to do reaction, and found that the methanolizations rather than beta-O4 cleavage occurred, and LCC bonds. In this under these reaction conditions, we found that almost all beta-O4 linkages were preserved with lignin extracted from the biomass. And this lignin with a structure well preserved can be effectively converted into phenol with a high yield more than 62%. And we investigate the effect of those three parameters on the lignin structure, and we temperature has a much higher effect on acid concentration and than on the time. The third work we used the followed by molten salt hydrate hydrolysis process. First one, firstly, the lignin cellulose were treated by dilute at a relatively mild reaction condition with assistance of microwave, and infected converted hemicellulose into xylose. And the solid with the cellulose and hemicellulose were treated by molten salt hydrate to dissolve cellulose and with lignin isolated. We found that after the two-step pretreatment, the lignin was the beta-O4 linkages in the lignin was well preserved, and the monophenous yield was pretty good. The biomass can be fractionated into cellulose, glucan oligomers, and a high yield of non-condensed lignin. In the future, non-condensed lignin, we are now doing some research on fundamental study to study the interactions between lignin and cellulose and hemicellulose, and such as new biophysics system or development or new reactor to in situ removal of cellulose and hemicellulose with the lignin isolated. That's thanks my advisor and my student and my group and the funding support. Thanks all for your this WeChat and my email. Thank you.
Thank you for the lovely presentation, Dr. Firstly, we are honored to have Professor Pan to share his insight.
Yeah, very nice talk too. As you mentioned, if you can isolate lignin without condensation, but retain beta-O4 linkage, would be very useful for different application. My first question is, can you go back to the first method you mentioned? It's use formic acid lignin, right?
Yes.
So that's 80 degree for
100 million.
100 with there's a small amount of hydrochloric acid. It just can extract 94% of lignin out.
Yes.
Otherwise, right?
Yes. Oh no. It's constant.
Constant over. Okay.
Yeah.
Oh, constant over. Okay.
Yeah.
Oh, that makes more sense. Okay. So the beta-O4, you think is retain
yes.
intact?
Yes.
Okay.
Mm-hmm.
That's very interesting. Hemicellulose was convert hydrolyzed into
a xylene.
Xylene. Okay. How about the third method? It's a combination of microwave assistant acid pretreatment to remove hemicellulose.
Yes.
And
molten salt hydrate.
Okay, that didn't cause any lignin condensation.
A little, you see here. This is the first step pretreatment, and beta-O4 linkages slightly decreased. And after the second step pretreatment, more terrible beta-O4 linkages cleavage.
Okay, so the second part is the molten salt hydrate.
Yes.
And use with or without acid.
Sorry.
So for the second state.
For no addition of any acid.
No additional acid.
Yes.
Okay, just a dissolved cellulose and hemicellulose.
Yeah.
Okay.
Hemicellulose was removed in this step, and without addition of acid, this one was pre-treated. It was treated by molten salt, and the cellulose was converted to glucan oligomers.
Okay.
So when it cooled down, glucan oligomer will precipitate. So I developed this thermal filtration, I call it. I designed it, and it can do a filtration at a relatively high temperature.
Yeah. Okay. Thank you.
Thank you, Professor.
Thank you, Professor Pan.
So I had a question for the corn stover, the first slide you showed.
Yeah.
One thing that's kind of surprising is generally the monomer yield is proportional to roughly the square of the beta of bores.
Yeah.
So here it's quite high.
Yeah.
Are you counting the acids in there too, like ferulic acid and coumaric acid and things like that in the yield?
You mean this one?
Yeah, because there's a lot of acids in the corn stover.
Yes.
Okay, so
Yeah.
that's probably where that comes from.
Okay. Okay.
But I'm surprised that the acids aren't broken down when you say the monomer yield. This is after.
No, this is after the fractionation. We got a lignin and use the lignin to do depolymerization at a high temperature.
How did you depolymerize it?
Rhodium carbon to do the depolymerization with a hydrogen on the high temperature at 180 degrees.
Okay.
And
do you know? Do the acid? I would be kind of surprised if the acids didn't come off during the reaction. Did you measure the liquid during the reaction?
Reaction? You mean
if I had 80% formic acid and the rest is water?
Yes.
The acids don't come off?
Seal is a glass reactor. And
but you analyze the liquid.
Yes, we analyzed the liquid and got this one. The one was dissolved in the liquid. Okay. We analyzed it.
But there's no ferulic acid or coumaric acid or things like that?
The for acid, maybe the formic acid is too high, so we didn't see the.
Okay. Yeah. Okay.
Right. Thank you for the great question and answer. Due to time constraints, we will need to move on. And this is the certificate in memory of this great. Thank you very much. Although we still have two presentations, but I think everyone need a refreshment. So shall we have 10 minutes a break? So like we come back by 4:28, and right. second session, and we still have 6 presenters. Please do keep your time and do a very perfect timing. So next, our next presenter is she's still in her very young research career, and she's still a PhD student. And her topic today is efficient fractionation of lignin cellulose by in situ deep I'm not sure. Eutactics, thank you so much. Eutactic solvents and the structure features of lignin from Cetum giganteum. Let's welcome.
Good afternoon, everyone. I'm honored to have the chance to share my work. First of all, let's introduce myself. My name is Dalian, PhD student, come from Dalian University of Technology. The title of my presentation is Efficient Fractionation of Lignin Cellulose by in situ deep eutectic solvents and the structural features of lignins from Penicetum giganteum. Firstly, we will come ground section. As we know, lignocellulose is the most abundant natural biomass. Cellulose, hemicellulose, and lignin, which together make up lignocellulose, are all suitable choice for the creation of bio-based materials. The cellulose and the hemicellulose with lignin to form complex structures. At present, various pretreatment methods has been developed to enhance the deconstruction of biomass. Each method has their own advantage and shortcoming. So how to achieve the efficient separation? Deep eutectic solvents has advantages of simple preparation, precise and high solubility through hydrogen bonding, and is an innovative green solvents for biomass separation. DS plays an important role in realizing the efficient separation of biomass, promoting the high efficient enzymatic hydrolysis and the recovery of lignin. Based on the background, the Penicetum giganteum as the material for 3 reasons. One, first, fast energy conversion rate, fast growth rate, and strong resistance. 3, PG might be an ideal biomass because the high content of cellulose and hemicellulose in PG contains about 42% glucan, which is different from costour. For previous work, the pretreatment of PG was investigated using the DS to obtain the sour sugars of lactic acid. The recycling of DES and the recovery of lignin also were investigated. In recent work, we found that in situ DES can reduce the time and energy cost, maintain a high delignification, solve the problem of DES easy to lose. Therefore, the aim of the present study is to couple the DES synthesis process with the pretreatment process. We pretreated PG using DES and in situ DES. Figure 1 shows that basic DES was most efficient solvents amongst the investigated DES for PG pretreatment. As a result, 94% and 73% hemicellulose were recovered, and 95% lignin was removed. The load of glucan and xylan were increased to 99% and 96% respectively. From the pretreated solution using different methods. For the results of this part showed three important information points. The recovered lignin contain a large amount of S and G units and a small amount of H units, which is consistent with purchased lignin. Second, the carbon dioxide methods for recovering lignin can return the structure more intact. And last, the in situ DES lignin shows the similar properties to DES lignin. Results of this part show that the in situ lignin was more homogeneous, and the rotation was more complete. More importantly, the recovered lignin proposed great antioxidant activity, which is industrial antioxidant BHT. Moreover, recovered lignins has a significant antibacterial effect on pathogenic bacteria. In summary, in situ DES can realize the efficient separation of lignin cellulose and is a great significance to develop an environment-friendly biomass utilization as well as the application of high-valued lignin. Finally, I would like to thank Associate Professor Sun Yaqin and Professor Xiu Zhi for their encouragement and guidance. Also, thank you to NLSTS Duty Lab for support, especially the organizing committee for giving me this opportunity to share and learn from all of you. That's all. Thanks for your attention.
Right, thank you, Dr. Xuan. Very good time. Firstly, we are very honored to invite Professor Wang to give her insightful thoughts.
Thank you very much. As a PhD student, I think you did very good work of presenting. But I have two questions for clarification. So as a DES, you named it as in situ DES. I'm not quite sure what definition represents for. I think you just put the HBA and HBD and your grass in one pot.
Yeah.
But how to justify as in situ DES apart from other DES, which makes it HBA and HBD first and then put with your grass. So that's
one page is
DS preparation. You put your hydrobond donor and acceptor first as a mixture, and then you use as a media to pre-treat. But now it seems like you just mix the three components together and call it in situ DES. So I'm not quite sure what that definition represents for as a name, as a definition. And the second is how do you harvest your lignin from the system after pre-treated? Like you use some solvent to. I think I missed that point.
对，是合成的。
对，第一个问题就是为什么好像跟别的 DS 合成好像区别不是那么大，我认为哈。第二个的话就是你怎么把那个 lignin 收获出来的？然后你的 DS did you recover the elements on the recoverability of the DES in this field？ 就是你怎么收获木质素的？然后你的那个 DES 有没有做循环？然后这块你可以 comment 一下。
可能会清楚一点，而且确实啊，
好的。
那个就第一个问题就是关于怎么证明它原味，然后 最开始的时候想用红外去表征一下，然后但是因为组分比较多，我就是也做了单一组分的，就是单独的 HBD 和 HBA 的，然后它的效果都没有它好，然后我们就以此来辅证它的一个氯化胆碱或者单独的一个乙醛胺等等一个方式。然后那个 DS 我之前做过一部分循环，它是可以保证有90%的回收率。然后还有那个我那个木质素的回收选用了水沉和乙醇沉淀以及通二氧化碳的方式，然后就比较可能就是方式。不是逐级，就是对分别的。就比如说我酸性的 DS 的话，我可能用水去沉，然后然后包括碱性的，我发现某一种组分它可以通过通过量的二氧化碳使它沉淀下来，所以我就做了大概这3种方式，8种木质素，然后就分别进行了表征。好，对，这个可能不是特别充分，
测了单组分，但 DS 其实可以双组分，应该是双组分或者3组分才能。
对，然后我们就是推测这个结果它会好的一个原因，是因为木质素也可能它在反应的过程中也能视为一个 DES 的一个新的组分，在这个过程中发挥作用，然后脱除。
Thank you for the very, very comprehensive question answer. We may have room for one quick question.
What is the definition of efficiency?
关这个。
You show the yield. What's the pretreatment efficiency? What's your definition of pretreatment efficiency?
Efficiency. 左边右边。左边的。那个三个方式，一个是4个方式，一个残渣保留率，然后纤维素和半纤维素的保留率，以及木质素的去除率，是来判断它的一个预处理的效率。然后右面的话是葡萄糖的得率和果糖的得率，来算它的一个酶解，就是我们把它那个预处理完的一个固体去过滤出来之后去做了酶解，然后发现它的酶解效率是其他的 DS 的方式以及不经处理的 PG 的这个与菌草的这个。
For example, and pretreatment efficiency, what does that mean?
80%。老师，这要看具体是哪一个参数，那可能就是我这个坐标的那个标示是不准确的，
实际上是4个指标，那不对。那 define。
好，谢谢老师，我回去就是再查证一下这个应该怎么表示会比较合理。
Right. Thank you for the discussion. Here is a certificate for you, in memory of your probably the first international communication, and a door for you to further academic career. And thank you. And then we will have Dr. Wang Shuizhong, who will share the research topic on atomically dispersed palladium for reductive catalytic fraction lignocellulose into alkane functionalized phenols. Let's give him a warm welcome.
Thank you.
Good afternoon, everyone. It's a pleasure to be here with you today. I'm Xu Zhongwang from Beijing Forestry University. The subject of my topic is paired palladium for RCF of lignin cellulose into alkene functionalized phenols. As we can see, my talk will be in 3 parts. To begin with the background, in modern society, fossil-based feedstocks are the sources for producing materials, chemicals, and fuels, but their exploitation has caused environmental concern. So using renewable biomass to obtain low carbon products is big. Lignin cellulose is the most abundant and renewable resources on Earth, which is composed of cellulose, hemicellulose, and lignin. Current biorefining model mainly focus on cellulose and hemicellulose for producing high value product. But the leftover lignin is regarded as industrial waste with more CC bonds and fewer bit-over linkage, making it difficult to transform. So thinking an effective method for converting lignin into high value-added product is necessary. Recently, ASEAN be an effective strategy for converting native lignin into phenols with high yield and liquid products. Meanwhile, the solid carbohydrates were left with high. During ASEAN process, high-loaded nanoparticle mineral catalysts were used, affording low and high functionalized phenols with ideal yield. However, the activity mental center in this catalyst have a low utilization efficiency, and the current are usually less than 30. In recent years, atomically disappeared mental catalysts have been developed for lignin depolymerization with catalytic activity and selectivity. But low functionalized phenols are the main product, which usually requires tedious steps for subsequent. Therefore, we reported an atomically disappeared PD catalyst for RCF of different lignin cellulose, affording high T1 and monomer yield and remarkable selectivity to high functionalized phenols. First of all, the character of PD carbon formed. SCPAS analysis showed that PD loading is 0.1%. Hard if STM and exact results confirmed atomic disappear of PD in this catalyst. Next, the PD carbon was applied to RCF of dust. Monomer yield was 40.7%, in which alkene functionalized phenols PPG and PPS the mean product with a selectivity of 62%, and the corresponding to surface area and pore volumes. After regeneration at integrated with PD carbon, giving PPG with a 9% isolated yield. Treatment PPG with graft to catalyst 90 degrees. Under solvent-free conditions, natural products were generated with 85 yield. The obtained considerable potential for the fabrication functionalized biopolymers. Finally, I would like to acknowledge the NLSTS, CPSF, and Beijing Forestry University. Okay, that's all for my presentation. Thank you.
So it's very interesting. One of the questions I had was about it's concerted. Why couldn't you have one of the hydrogenolyses followed by a dehydration? I'm curious at how you think the double bond forms. It's not there in the beginning.
Double bond.
The double bond is not there when in the lignin, right?
Yeah.
So you said it's concerted, but why? Maybe you can go back a slide. Back one more. According to your analysis, no, you can stay on the. So according to your analysis, you have deuteriums everywhere, but you could still get those if you had a hydrolysis of the CO bonds in the beta O4, and then a dehydration of the alpha. Right?
Dehydrogenation alpha.
A dehydration. So your OH dehydrate. Your alpha, that one.
Yeah.
If you break the first one and then have it, if you do first one and then do dehydration on the alpha.
Oh.
So you remove a water.
Hydrogenolysis 是 CC double bond words form the bond.
So I guess what I'm confused about is the formation of the double bond.
C alpha.
So you say, if I understood correctly, you say everything kind of happens at the same time. You cut and you form. It's concerned.
Okay. I think
I don't know if my question's clear.
Yeah.
Sorry, yeah.
Yeah. Confirmed. Yeah.
Remove the water.
That's possible.
Yeah. That's understandable.
What because if that's true, then your catalyst should have dehydration abilities for other model compounds. You could sort of test that. Secondary OH groups.
用过啊，对。The model lignin was tested in was performed. Sorry, this question not considered precious.
I think because you have zinc oxide in your catalyst, we observe like a similar like double bond between alpha and beta oxide as well. Actually, we use the beta O4 model components, so we can observe a lot of ether bonds. So if you look at the literature from some like a popping process, so I'm not talking about say during the popping process, we have looked at the literature. There are some of from very early literature showing that ether like the double bonds can form if you have alpha OH or even gamma OH. So because you active the right there, you attack the OH group. Yeah, very easy. And then as you say that you can remove one water and and then they form the double bond between alpha and beta. So if you want to find the evidence, so what you can do is like for us, we just like separated the intermediate with the time increasing. You check you use the HPLC or GC mass. Like for us, we use the HPLC. Yeah. So we found like the peak. So we connect that peaks. We use the HMR. So we found the inner ether structure. So I mean, because this is oxidizer as well. So I don't know if it helps.
Well, sorry, but no, this is interesting. So because if you hydrogenate the alpha first and you keep the gamma, if you dehydrate, this is something we've seen. You will immediately rearrange to that because the terminal double bond is not stable. There's something interesting in the mechanism. I'm sorry.
Thank you so much for the very deep and constructive discussion about the mechanism and action path. So we will have to move on. And thank you again, Dr. Pong. And here is the certificate in memory of this great moment. Thank you. Right, our next presenter is Dr. Hu Yancheng, who will be sharing his research on biomass-based of polycarboxylic acids and high energy density fuel. Let's give a warm welcome.
Okay, good afternoon, everyone. My name is Hu Yancheng from China University of Mining and Technology. Today, my topic is biomass-based production of polyacids and energy density. My topic following 4 parts. First, to address the climate change, developing biomass supply chain petroleum supply chain facilities to build a no carbon society. In recent years, bio-based polyester such as this is the acid which can focus on production or because it also shows so for practical applications we chose IRA as the best catalyst. And also we also tune the hydration reaction. We also found that in the presence of palladium, carbon, and HY can at a high temperature facilitate the so with this from fructose, they produced furan and aliphatic diacids with fructose. Also with 3 steps and about 60% overall yield. And my second my high energy density fuel. High energy density fuel often with density greater than 0.9 is the platform. And with this, we chose such as cyclohexanol and benzaldehyde or cyclopentanol. We develop reaction and such as DA reaction and also production of fused tetracyclic fuel. Because butane often consists of four rings, but so we want to prepare a fused tetracyclic fuel. The focus is the dehydration of vicinodiol from cyclopentanol, and the challenge is often in common organic solvents, often spiral rearrangement pathway is dominant. But when we use ionic liquid and the Dalian, besides this, catalyst also shows good usability for this reaction. And following DA reaction, Following DA reaction and hydrodeoxygenation can produce fused cyclic fuel, and which possesses better property petroleum fuel. In conclusion, we use levulinic acid and fructose. We develop a three-step route for production of a series or alkyl acids and furan-based acids. And also by rational design of compact polycyclic structure, we prepared a series of HED biofuels. Thank you for your attention.
Thank you, Dr. Fu Yan, for the very nice presentation. Firstly,
okay, due to time limit, probably I'll just ask a quick question because I'm an engineer, so I'm quite interested in your process. So for the second work, you use ion liquids as a catalyst.
Yes.
I think it will be homogeneous reaction with your products and the feedstock. So how would you recycle and separate your ion liquid catalyst from the system?
Actually, this Lewis acidic acid is not soluble in our system because we use we use toluene as solvent, so we can recycle this by simple decantation.
Liquid face to face.
Yes. Yes.
And how about your products after reaction? It goes to your which phase?
In organic phase, not in
liquids.
yes.
So it will be just separate.
Yes. Yes.
okay. Right, we still have room for one more quick question.
You demonstrate multiple approaches to synthesize the acid and bio-based precursor for jet fuel.
Yeah.
And are you by chance done any TA and LC for any of these products? So
Yeah. Yes. We also cooperate with other groups. So we want to do some LCA or TA analysis to evaluate our economy or greenhouse gases emissions. But this work is ongoing in our laboratory.
Right. Yeah, the time is already gone. So thank you again for the very insightful discussion. And we have a certificate in memory of this moment.
Okay.
Thank you. So our next presenter is Dr. Zhang Qiaoya. Zhang Xiaozhi, sorry. Dr. Zhang Xiaozhi will share the research on fabricating biochar catalysis for microwave-assisted oxidation of glucose to value-added organic acids. Warm welcome.
Thank you. Good afternoon, everyone. I'm Zhang Qiaozhi, a research fellow from the National University of Singapore, and I'm recent studies about fabricating low-cost biochar catalysts for microwave-assisted oxidation of glucose to organic acids. As we all know, biomass is a renewable and carbon-neutral resource. It is of huge potential, but underutilized currently. Paralyzing the most abundant lignocellulosic biomass to biochar is one of the most promising strategies to utilize biomass resource. The product biochar can be used in versatile fields and contribute sustainable development goals. The product biochar is has tunable characteristics such as functionalities, carbon matrix, and porous structure. So it can be a promising support for catalysts. And for about the microwave is a type of electromagnetic wave, and it can be absorbed by microwave absorber, such as the carbonaceous material. and it can be absorbed and converted to thermal energy and achieve volumetric and rapid heating, conventional heating. For the microwave responsive material, carbonaceous compared to other carbonaceous material, Beltra has superiorities such as the low cost, the carbon neutral feature, and the tunable characteristics as mentioned before. So we fabricated a different transition metal-based Beltra catalyst to the oxidation of glucose. The first study is to produce sugar acids from glucose using Cooper Beltra. The product include gluconic acid and glucuronic acid. Both acids can be used in extensive applications. But currently, in previous studies, noble metal catalysts are required, and base is essential to achieve high yield. So in this study, we use low-cost Cooper Beltra catalyst and base-free catalytic system. We fabricate a series of and we found that the Cooper Beltra with 1% of Cooper loading and synthesized at relatively low temperature, namely say 600 degree, has a relatively high catalytic performance than others. So we need to know about how it happens, about the active site, the roles of Beltra, and the roles of microwave and reaction pathways, because the substrate and the product has different conformations. And based on characterization results, we can determine the active sites could be the Cooper 1 oxides and the metallic Cooper, because the catalytic performance increase with their contents. As for the Beltra support, we can find it is mostly determined by the pyrolysis temperature. With the increasing temperature, the oxygen functional group decreased, while the degree of graphitization and aromatic ring condensation and surface area per volume increase. These can to the capacity of material to the absorption of microwave, then achieve rapid heating of the catalytic system and achieve an energy efficiency process. But can also see the contribution of microwave by normalizing the energy consumption per converted glucose, and we found that the microwave cannot be totally utilized by the reactant. About the reaction pathways, we can see there are two conformations of glucose in the solutions, and there are two pathways with and without ring opening process. Using DFT simulation approach, we can find synergistic effects of Cooper 1 oxide and metallic Cooper. The copper oxide mainly contribute to the cyclic glucose ring opening step, while metallic copper plays important roles for the functional groups oxidation. The next part is about the glycolic acid production using manganese belcher, different from the sugar acid production. Glycolic acid is a shorter chain organic acid, and it is also a versatile compound. And a huge market, but its industrial production relies on fossil resources. So we need to develop a catalytic system, produce it from renewable resources, namely the glucose-rich biomass resource. In previous species was found to be able to improve selectivity to glycolic acid and has been reported as active sites, but the specific active species are still unclear. In this study, we found we also fabricated different manganese belcher catalysts at different pyrolysis temperature and from different precursors. We can see the precursors manganese 7 shows more effective performance than manganese 2. And we also studies active site reaction pathways and roles of belcher support. And by correlating the catalytic performance with the manganese 3 proportion, we found that this is dominant species for the catalytic process, and the belcher roles are similar as previous studies, but we can see the effects of the oxidation by high valent manganese 7 precursor, and this contribute to a more microwave higher ability to absorb microwave. And we also found the reaction pathway is mainly the retroaldyl reactions. The formation of glycolic acid from glucose is dominantly the retroaldyl reactions, but the formation of fructose, it is unavoidable, but the formation of byproducts via fructose, the byproduct formic acid is also a valuable product as a safe hydrogen carrier. This catalytic system can oligosaccharides. Due to the time limit, I didn't go into too much details. Please feel free to ask me. Thank you.
Dr. John. A very good presentation. Shall we have a little back and forth on this?
So I'm curious with the microwave processes, is the enhancement you see when you use microwave? So have you do controls where you just compare it to rapid heating? Can you do controls like that?
In other studies, they do comparisons using conventional hydrothermal reactions and microwave reactions. But in my study, I didn't do the comparison.
But do you think if you do get an enhancement, is it because of the microwaves themselves, or is it because you get local hotspots?
About first, we use the microwave to achieve a higher energy efficiency. This is, I think, this is the most important effect. And for the roles of hotspots, there is the researchers didn't get agree about this because some findings indicate the effect of hotspots to like reduce the activation energy or something like that, but some findings didn't is not consistent with this observation. So I think there might be some chemical like promoting effects about electron transfer, but the contribution to the reaction, it is still doubtful, in my opinion. Yes, that's all.
And a similar question, I think, that was asked earlier today. What's the benefit of using biochar versus a typical activated carbon?
Oh yes, it's I think it is engineer applicable and very low cost compared to activation carbon, and the contribution to environment because it's a waste derived catalyst. So I think the contribution to environment is also important.
No, I agree with you. So but there's no real reaction benefit. It's more the sort of life cycle of the process.
Yes,
okay.
yes.
Okay. Okay.
Thank you.
Thank you.
Thank you so much. Very, very good timing. Thank you again for the discussion. We have a certificate memory of this moment. Thank you so much. And next presenter is Dr. Chen Lu, who will be sharing the research on reductive depolymerization of lignin and Zaszin's in the studies. Let's give her a warm welcome.
Okay, great. Hello everyone, and I'm Lu Chen. I'll briefly introduce myself. I had my PhD in EPFL with Professor Paul Dyson, and later moved to UCL, continues as postdoc, and now I was a Wiradner. And it's such a pleasure to share with you about our work on reductive depolymerization of lignin and some synchrotron techniques in mechanism studies. So as we all agreed that the lignin has a huge potential to produce a bulk aromatics through cell bound cleavage. I hope there's no question mark about that statement because I got some negative comments about that in other conferences. We have a lot of efficient catalysts to breaking the cell bonds, even the CC bonds. But there is a debate about how the cell bonds cleavage, it can through either surveillances or hydrogenolysis. To figure it out, some of the group proposed such basket strategy and kind of like a tea bag to separate the catalyst from the lignin part. A typical British way, right? So it's kind of British's favorite tea bag. And my PhD advisor loves it because he's a British for sure. And what we have seen as a scientist is those pores are relatively large as it's in millimeter scale. So that leads to our project to improve such separation strategy for rhodium nanoparticle, the hollow carbon sphere. It got nanometer pores over it. So what we expect is the lignin polymers cannot enter through those relatively smaller pores, so that it cannot contact with the rhodium nanoparticles, while monomers and dimers, those small parts, can come through those pores and then contact with the rhodium nanoparticles. Thus, we know whether the rhodium nanoparticles participate in breaking the cell bonds or not. First, to prove our assumptions, we used our narrow reactor structure in a lot of monomers and dimers hydrogenation reactions to prove that those small molecules, they can pass through the pores and goes inside the nanoreactor. And then to prove that lignin cannot go inside, polystyrene with different molecular weights were used as a molecular probe. Compared with rhodium on carbon, our catalyst can preserve all the aromatic rings, which means those polymers will not be able to enter through those small pores. And then let's see the performance. It's not bad. So for us, those nanoreactors offered similar monomer yields with rhodium on carbon, the commercial catalyst. So we're thinking about that the lignin cannot contact with the rhodium nanoparticles while afford a remarkable monomer yield. That means in this system, surveillance is probably responsible for breaking the Thiel bonds cleavage. And then during this project, we found out that sometimes during the harsh reaction conditions, aromatic rings probably were hydrogenated. Then we want to preserve all the aromatic rings. That's the beauty of the lignin. So we proposed the single atom alloy catalyst, which the platinum single sites were doped in the nickel nanoparticles. We expect that the hydrogen were dissociated over the nickel sites and then spill over to the platinum side and desorption and reaction here. With STEM and exhaust, we prove the nature of the platinum single sites. With only 0.1% of platinum, at 200 degrees, we got around 40% of the lignin monomers, which is considerably high carbon. After exploring about the catalytic studies, we want to move forward to the more about the mechanisms. To build a holistic system for mechanism studies, we used lots of different operando in situ techniques in different time or spatial scales to evaluate the mechanism part. First example is about we compare the surface alloy with the normal alloy. So for the platinum was only on the surface of copper nanoparticles. As for the normal alloy, platinum was randomly distributed inside or the surface of the copper nanoparticles. They have exactly the chemical composition, but the catalytic performance are different. So we're trying to figure out why and how it happened. Then after ruling out the internal and external diffusion effects, we use operando things, XAS, to evaluate the redox and platinum species. And for the copper and platinum in the surface alloy, it has much better redoxability, and which is consistent with our NAPSAF's techniques, which is more towards to a surface technique. So with both two techniques, we conclude that the higher, the better the redoxability leads to the better activity. And then we also know that not only the redoxability matters, but also the redox. So we use EDE to quantify the redox rate of copper species. And for after the test confirmed that the surface alloy do not only have the better redoxability, but also higher redox rate. And we can compare the reduction rate of copper 2+ and the oxidation rate of copper 1+. Then we can find out the reduction is much slower than the oxidation step. So probably we're guessing the rate determining step is the reduction of copper 2+. Then we know that the redoxability is quite important for the activity. They want to look more into how we can adjust the redoxability. Then we use different techniques, including XPS, Hershey length, and valence to band to look into the electronic structures of the copper oxide. And then we conclude that with the higher occupied state and lower unoccupied states, we got weaker copper oxygen bonds, which is easier to break and form, and thus leads to better redoxability and then the higher activity. Now, finally, we also compare to see the copper structure, how it affects the reaction. Then we compare with the single sites with copper nanoparticles with operando XAS. We not only confirm that the redoxability matters, but also we can identify the active intermediates in our system. And thank you. I would like, last but not least, thank you for all the supervisors and courses, colleagues, and also for Marie Curie or SF for the financial support. And I'm open to all the questions. Thank you.
Thank you again, Dr. Chen. So firstly, we honor to have
I have two questions.
Yes.
First question, firstly, very nice presentation and very nice work. And you're talking about your nanoreactor.
Yes.
But you're talking about the pore size because you want to make sure the lignin not come out with your nanoreactor, right?
Yeah.
So you use the polystyrene. So my question is like, what is molecular weight of your polystyrene? Because like lignin depends on they probably like high range of the molecular weight. So this is first question I have. What is the particle size of your molecular weight of your polystyrene you used for your experimenter? So so how can you make sure like your lignin not coming into your reactor? The second question is in your slide 12. So you mentioned that you compare with the single atoms with nanoparticles. So I know single atoms, you probably need to use like extremely lower concentrations, right?
Yes.
Yeah. What is the concentration you use so far? So when you prepare nanoparticles, you choose pick of nanoparticles. But based on my experience, we think like you can get, if you got extremely low concentration, you got single atoms, right? On your catalyst. But anyway, if you want to prepare nanoparticles, sometimes you cannot avoid, your system probably still have single atoms, because I look at your image, that is STM image, right?
Yeah.
So I only see you showing like nanoparticles. Did you observe some like that's
Thank
my
you for kilowatts and 30,000 range, but we couldn't get lower than the 3,000 ones. So
that means more than 3,000, right?
hopefully we use sawdust. So in this system, we use the pure sawdust.
Okay.
So it should be larger than 3,000. So it's completely
so
untreated.
What is your nanoreactor looks like?
Here. So you can see those rhodium nanoparticles, those carbon sphere.
Say it again.
Those black dots, they're rhodium nanoparticles. They're inside of the carbon sphere. This is the carbon sphere. It's kind of a hollow. Yeah, the hollow structure. So the rhodium nanoparticles are inside of the carbon sphere. Yeah.
So you synthesize this hollow structure, right? Okay, so you think your lignin will be inside your...
No, lignin will not go inside.
Oh, go inside.
Yeah, it will not. So we're just wondering about lignin cannot contact with the rhodium nanoparticles, but it still degrade. So that's the reason we want to see what happens.
Okay. Okay. So your like the entire system, hollow structure is your catalyst, right?
Yes.
Okay. So I'm curious how you make this catalyst.
This is a hydrothermal process.
Oh, hydrothermal
So
process.
yeah. Okay. And afterwards, it's like to burn everything to do carbonization.
Okay.
And for the second question, it's related to the single size. Yes, we definitely cannot avoid about the single size when we have nanoparticles. So we use EPR to quantify the copper single size. So we can see here the carbon single size also around 80%. So they are 20% of copper, they are not in single sites. Yeah, this is just dominated by single sites, but they still copper, they are still in the form of small clusters, which cannot be seen in the examples.
Like lower concentration, right?
This is 4%, so it's relatively high, yeah.
So showing like you have 80% of single atom, 20% of
No,
nanoparticles.
yes.
How about like this one? The nano
This one is also a kind of opposite. It's like most of them are nanoparticles, but still there will be more than 10% are in single sites. Yeah.
Okay.
And also examples cannot see. So that's very tricky. So examples not versatile in distinguish the copper single sites and clusters. So even there will be 20% of the single sites in examples, we cannot see it.
Yeah, but STM can see very clearly.
Yeah, but in our system, it's because copper was heavier than the SM is made by the alumina and the silica. So yeah, it's also challenging to see by, yeah.
Okay.
Thank you.
Thank you again for the very deep discussion about structured characterization. So just move on to the next, and here is a certificate for you in memory of this moment. Thank you. Right. So our final presenter is Dr. Yu Yumiao, who will be sharing the research on metallic glass facilities, lignin CO. Let's give a warm welcome.
Good afternoon, everyone. I'm Yu Miaorui from Institute of Process Engineering, Chinese Academy of Sciences. For the presentation opportunity. Thanks the staff for their hard work. My presentation is metallic glass facilitates lignin carbon oxygen bond cleavage. The presentation includes 3 parts. Lignin is the main component of biomass and abundant aromatic resource on our planet. It's utilized automation. To fully utilize lignin, we have developed many methods. Simply speaking, these methods can be divided into 2 types. One is the direct use of lignin to fabricate lignin-based materials like adhesives, hydrogels. And the other one is the lignin degradation to produce high-value chemicals and fuels. We know lignin structure is very complex, and the carbon-carbon oxygen bond cleavage are very challenging. Recently, electrocatalytic degradation has shown great potential. It uses renewable electricity, works under mild conditions, and the reaction and products are controlled easily by the reaction voltage. For the electrocatalytic reaction, the catalyst and the electrolyte are 2 important factors. Here, we summarize some metallic catalysts reported in literature, and we can find that noble metals are widely used. They are effective, but we have to consider the cost effect. So the effective catalyst has always been our goals. As for the electrolyte, alkaline and acidic solutions are often used. Some organic solutions like DS and ionic liquid are also used. Lignin very well, and they are more environmentally friendly. Sometimes we call them green electrolyte. And based on these results, we mainly focus our work on catalyst design and the first work is carbon oxygen bond cleavage by crystalline catalyst. For electron reduction, noble metals are more effective, so we synthesize the different kinds of binary and ternary catalysts. And the SPS results show that nickel doping induces electron redistribution, and palladium metal is more electron rich. After electron reduction, we find that the palladium nickel bismuth has the highest conversion ratio and product yield. That's because it has the lowest interferon impedance and the largest potential for HER. And then for the electrolyte, we use ionic liquid. It can dissolve lignin very well. For the 5 typical ionic liquid systems, we find that imBF4 diluted by organ organic solvent has the largest conductivity and has the best degradation results and was chosen as the electrolyte. Then we tried different substrates on this electrocatalyst system and find that it also well. For the substrate with the carbon group on the alpha carbon position, the conversion and product yield are both very high. Carbon group, the conversion drops to 0. So we can obtain the conclusion that the carbon group is closely related with the degradation process. The oxygen atom obtains from the electrode, and then the substrate was characterized into monomers. We also performed the DFT calculations and find that the rate determining step is the desorption process for the phenol product. And the palladium nickel bismuth catalyst has the smallest energy barrier because it has a lower charge transfer between the catalyst and the product. So this work shows that the crystalline palladium nickel bismuth catalyst in combination with ionic liquid electrolyte achieves carbon oxygen bond cleavage of lignin dimers. The work is carbon oxygen bond cleavage by metallic glass. Normally, for catalyst design, we mainly focus on crystalline structure. But recently, in some studies, that amorphous structure has some advantages over crystalline structure. For example, it can expose more active sites. And metallic glass, as a typical of amorphous metallic, can be prepared by melt spinning method. And the obtained glass ribbon has good elasticity, can be wrapped around the solid surface to serve as electrode and catalyst. It's very stable and can be recycled dozens of times. We synthesized the 3 kinds of palladium-based glass ribbons, and the most amorphous structure was confirmed by the experiment. And then we chose the electrolyte based on the CV curve. We also use the ionic liquid electrolyte and find that the IMBF4 ionic liquid has the lowest peak potential and light. And for the prepared 3 kinds of metallic glass ribbons, the palladium 30 has the largest peak current and was chosen as the catalyst. And then in the degradation experiment, for better product selective yield, we further optimize the electrolyte from a ternary system to from a binary system to a ternary electrolyte composed of ionic liquid, methanol, and water. The ionic liquid is for conductivity and methanol for lignin dissolution, water for proton transfer. Electrolyte, the conversion and product yield are both very high. Based on simulation, we find that in this ternary electrolyte, 2 lignin molecules have a favorable action. And then we change the pH value of the electrolyte and find that for an acidic condition, the product obtained as a neutral condition will be first generated. The carbon group transforms to a hydroxyl group. Note that the benzene structure was maintained and without over-hydrogenation. We find that the pH value affects the hydrogenation process. pH value of 0.3 and a voltage of negative 1.5 achieves the best product yield. And the selectivity was as high as 99%. From the reaction curve, we can see that in the initial process, the product with the carbon group further increases and then decreases. At the same time, the hydrogenation product increases. So we think that it's a cascade hydrogenation process. We then tried different substrates with this electrocatalytic system and find that the cascade hydrogenation applies well. For the neutral condition, the conversion and product yield are both very high. The substituent affects the conversion rate. If there is a substituent on the ring of A, then the degradation rate decreases rapidly. So we think that in the absorption process, the absorbed on the catalyst surface, and the substituent on it increases the stereo cadence and decreases the conversion rate. Then for the that the conversion and the phenolic product yield was very high, but the hydrogenation product varies, especially this substitute on the ring A, the hydrogenation product increases rapidly, and the hidden mechanism is under investigation. And finally, we compare the degradation performance of the amorphous material with the corresponding crystalline catalyst and the commercial palladium carbon catalyst, and find that no matter for the product yield or the selectivity, the metallic glass ribbon perform better than the crystalline catalyst. And due to determining step, metallic glass ribbon has a lower energy barrier, and the more active sites will be exposed for the subsequent hydrogenation process. That's why the material is better. And finally, the conclusion part. And that's the foundations from the Natural Science Foundation of China. And that's.
And we are honored to invite Professor Pan.
Thank you very much for your interesting talk. It's late and looks everyone is tired. I'll keep my commenting short. You use the Lignin model compound to demonstrate either bond cleavage. Have you tried any of your catalysts on real lignin? That's the first question.
Yeah.
The second one, did you try your catalyst to a model compound with the methoxyl group? Can you or the methoxylation? That's and another short comment. Can you go back to the second slide?
Second.
The second slide, I think.
This one?
The second.
This one?
Yeah, the next one. Next one. No, the previous one.
Previous.
In the introduction, maybe. Oh, yeah, here.
Oh.
So you use the simplified structure to show cellulose and hemicellulose. I would suggest you correct it. You use that's not sugar ring.
Oh.
In sugar ring, you should have oxygen. So that's the hexane ring.
Okay, thank you.
That's not correct.
I will change it later. Thank you. Thank you.
Yeah. Now you can come the question.
As for your first question, after we find that the electrocatalyst system works well, and in fact, we tried the real lignin, the birch lignin, and after degradation, we find that the molecular weight decreases, and we did detect the phenolic product, but the total yield was not very high, about 10%. As for your birch lignin, I'm sorry, the second question.
Did you see any demethylation, demethylation effect of your catalyst? For example, you have the that's the big
dimerization. For the first and the second work, we observe the dimerization, especially for this product. If we increase the reaction voltage or increase the reaction time, this product will dimerize.
No. Well, if you have a methoxyl group, think it will benzene.
Oh, yes, the different substrates. You mean the different substrates, the methyl group, the R1, R3, R4. We have the O0 methyl group on it and find it degrade well, both on this ring and on this ring.
My question is, can you leave either one?
Until now, we didn't find this phenomenon. As for third question, and since we mainly focus on lignin, and for the cellulose or hemicellulose, maybe I'm not very familiar, and I will. Yeah, thank you. Thank you.
Thank you all again. And here is a certificate for you. Right, so that's the end of today's session. I would like again express my gratitude to all of you experts participants and the presenters' engagement and your insightful thoughts has truly made today's sessions inspiring. And I hope today's thoughts will inspire further research. And thank you. So for please on the ground floor and we will take the shuttle. Thank you all.